All right, everybody, so our second set of formulas here is also going to be taking a look at independent and dependent events. This time we're going to be looking at conditional probability. So this is what we were looking at with those frequency tables, except the difference now is that we are going to be looking at these not only with the frequency tables, but specifically with just some calculations and formulas. So first formula for independent events. So again, this is events that do not impact each other in any way. If we have the probability of A and B, this equals the probability of A times the probability of B. So a simple multiplication problem. If we have dependent events, though, the probability of A and B is now equal to the probability of A times the probability of B. Sorry, I wrote that wrong. The probability of A times the probability of B given A. And then the third formula that we need is, well, how do we find the probability of B given A? This is a combination of other probabilities. It's a probability of A and B over the probability of A. So these two are basically the same thing, just algebraically rearranged. As you can see, if you multiply by the probability of A on both sides, you just end up with this formula here. But again, they interrelate. Sometimes you have some of the pieces, not all the pieces. That's why it's important to know both of them. But this kind of threshold is for dependent events here, and then the one on top is just for independent events. So let's take a deeper look at these formulas in action. So we'll go through some more examples, actually some pretty similar examples to what we did before, just with some new formulas. So for our first one, let's say event B is rolling an even number on a six-sided die. So once again, out of 6, we have 3 even options, and event A is simply, again, rolling a 2. In this case, 1 out of those 6 options is that. We again know the probability of A and B because this is where they both come together. Where do they happen at the same time? So in this case, it's 1 out of 6. So because of that, we can now find the probability of A given B. So this will just be the probability of A and B over the probability of B. So it looks different from up top, but that's because A and B have switched places. So because A and B have switched places, we now use the probability of B on the bottom instead of the probability of A. So probability of A and B is 1 over 6. The probability of just B is 3 over 6. So now we can do some division. So we have this probability equals 1 over 6 divided by 3 over 6. Division rules say keep, change, and flip your fraction. So keep the first one, change your signs multiplication, and flip the second one. We'll get 6 over 18, or 1 over 3, as our final answer. So again, the first thing we need to do is kind of set up everything that we know. And once we've set that up, step 2 is to plug into the formula that we know. So let's keep going. Some more examples. All right. So our next example, we'll say event A is a face card, and event B is a spade. So if we're looking at a deck of cards, the probability of drawing a spade is 1 out of the 4 types of suits. The probability of drawing a face card is 3 of the cards out of the 13 different types of cards that we see. Now the probability that we get both of these is basically asking us, when do we have face cards that are also spades? Well, of the face cards, 1 of each of them will be a spade, out of a standard 52 card deck. So that is our basically the two of those together. So if we're looking for the probability of A given B, so the probability that you draw a face card given, we're only looking at spades, we'd set this up with the probability of both of them on top, and we divide it by just the probability of event B, which in this case is 1/4. So once more, some fraction division. Keep our first term, change our sign, flip our second term, and we'll get 12/52, which actually reduces here to 3/13. So in this case, the probability given that we just are looking at spades, that we draw a face card, is actually 3 of the 13 spades are face cards. So that actually kind of logically makes sense. We'll finish up here with an example from flipping a coin, and if we're looking at rolling a die. So let's say the probability we get tails is 1/2. The probability we roll a 6 on a standard die is 1 out of 6 outcomes. So if we're looking for the probability, we do both of these at the same time. So in one hand you have a coin that you flip, and in the other hand you have a die that you roll. What's the probability that we get both of these, both a tails and a 6? Well, we just take them and multiply them, and we'll get that final answer of 1/12. We can use this formula because these are independent events. We'll do one final example of some dependent events. So now, what if we are looking at the probability that we have a 2 and an even number when we are rolling a die? So in this case, we want to take a look first at probability of rolling a 2 is 1 out of 6. The probability that we get 2 and even at the same time is 1 out of those 6 outcomes. So the last thing is, what if we have another probability that they're asking us? The probability that we get an even number given we've rolled a 2. Well, now we can go through and plug these in. And let's go back up to that original formula, and that's going to help us with how we find this. So we'll do the probability of them both over the probability that we roll a 2. So in this case, it's 1/6 divided by 1/6. So that helps us to set these up. So again, we know this, and we're asked to solve for this. So if we do this, we'll have 1/6 divided by 1/6, and in this case, KCF once more, 6/6 equals 1. And if you think about this logically again, the probability given you roll a 2 that it's also an even number, well, 2 is an even number. So every single time you roll a 2, it's going to be even. All right, so some examples to talk through. I know that these probably sound pretty confusing, so if you have to go back, watch the video again, take a look at the formulas, I definitely encourage you to do that today. Again, the calculation